In 1926, a French inventor secured a patent for a device that tripled agricultural yields. There were no chemicals and no heavy machines involved, just copper and zinc, drawing energy from both the sky and the soil. A British government committee spent nearly 2 decades reviewing the results, only to stamp every report not for publication and seal them away in a vault. The devices vanished. The inventor's name was scrubbed from scientific journals, but the patents remained. The laws of physics never changed. Over the next hour, you are going to see exactly what was suppressed and why. These are 4 forgotten sciences exposed one by one. This is the forbidden physics of gardening. Justin Christofleau was not a famous name in the world of science. He was a farmer, an experimenter, and a persistent tinkerer born in France in 1865. By the early 1920s, he had spent decades pursuing a single idea: that plants could flourish not just on nutrients from the soil, but on invisible energy drawn from the atmosphere. He dedicated his life to building unusual devices, metal rods, spirals, and antennas, staking his reputation on results that challenged agricultural orthodoxy. On October 26, 1925, Christofleau filed a patent in Switzerland for what he called the electromagnetic ptero-celestial apparatus. The document, stamped CH-186 and granted the following May, described a system of copper and magnetic steel plates designed to capture atmospheric electricity and channel it into the earth. This was not some backroom theory. The patent is still on record, a legal artifact that spells out every wire, every plate, and every connection. Christofleu's drive came from the fields themselves. He claimed that with his device, oats grew 5 feet tall and old. Dying trees burst back to life. He published his findings in books and agricultural journals, inviting scrutiny from anyone willing to visit his experimental gardens. The press in France covered his work, sometimes with skepticism, but often with wonder at the photographs and diagrams he provided. For Christofleau, the proof was always meant to be public, measured in harvests rather than secrets. Long before the rise of chemical fertilizers, he believed that nature already provided everything a plant needed, if only we knew how to listen. His patent remains a silent witness to a forgotten chapter in the science of growing food. Photographs from the mid-1920s show vegetables that seem to belong in a different world. Pumpkins wider than barrels and cabbages nearly as tall as a person. These images, published in Justin's books and pamphlets, fueled rumors of a breakthrough that defied every rule of soil science. The photos ran in French gardening magazines and local newspapers, often paired with claims of harvest twice the usual size and sometimes even more. Yet outside of Christofleu's circle, few could say where these pictures came from or who had verified them. The British Electroculture Committee, established in 1918 under the Ministry of Agriculture, took notice. By the early 1920s, the committee was gathering reports, reviewing crop images, and sending observers to sites across Europe. Their mandate was simple: separate fact from fantasy. Over nearly 2 decades until 1936, the committee collected field photographs, yield records, and testimonials from inventors like Christofleau. Their interim reports, stamped not for publication, cataloged everything from giant barley stalks to the peculiar devices sprouting in French gardens. Despite the striking visuals, the committee's files reveal a pattern of unanswered questions. No original negatives or third-party validations for the most dramatic images ever surfaced. The photographs, while persuasive, always seemed to hover between evidence and legend. For every snapshot of a bumper crop, there was a lingering doubt. Could a simple wire and rod truly explain these harvests? The visual record demanded an explanation. The search for scientific proof was only just beginning. Every patch of open ground, from city parks to rural fields, sits beneath an invisible river of electricity. The air above our heads holds a steady charge, positive in the sky and negative in the soil below. Physicists call this the atmospheric potential gradient. On a clear day, the difference between sky and earth is about 100 volts for every meter you climb. It is not lightning or a jolt you can feel, but a silent voltage always flowing like a gentle tide. Plants stand right in the middle of this field. Their leaves and stems, covered in microscopic hairs and wax, act as natural conductors. Each blade of grass and each bean sprout quietly collects electrical charge from the air. Roots buried in the earth connect to the negative pole of this giant natural battery. The plant itself becomes a living antenna, bridging the gap between sky and soil. This is not just a poetic image. The flow of electricity is measurable. In some experiments, a copper rod driven into the ground will register a faint current, proving that the air and earth are exchanging charge even on a calm day. The voltage gradient can change with weather, but the basic pattern holds. Sky positive, earth negative. A difference that never sleeps. For most of history, this background field went unnoticed. But in the early 20th century, experimenters like Christofleau wondered if plants needed more than water and nutrients. They asked whether this silent current could be tapped, harnessed, or amplified. The idea was simple. If every plant is already an antenna, what happens when you give it a better one? A copper wire, for instance, is far more conductive than a stem or a leaf. Planted in the ground, it can pull in atmospheric charge more efficiently, channeling it right to the root zone. The Earth's natural electric field is subtle, but it is always present. Understanding this invisible energy is the first step toward grasping how a single wire might change everything in the garden. Inside every plant, a silent conversation unfolds in the language of electricity. Roots, stems, and leaves don't just carry water and nutrients. They transmit tiny electrical signals known as action potentials and variation potentials that ripple through cells at the speed of life. These signals are not random. They act as messengers, triggering changes in growth, photosynthesis, and even how a plant responds to stress or injury. When a tomato leaf is wounded, for example, an electrical wave travels down the stem, alerting distant cells to prepare their defenses. This is plant physiology at its most basic, a living circuit tuned to its environment. Researchers have measured these signals using fine electrodes, charting the flickers of voltage that pass from cell to cell. Even a faint field, just a few microvolts per meter, can spark a chain reaction. The plant's internal wiring responds to changes in its surroundings, whether from sunlight, wind, or the subtle pull of the Earth's electric field. Some studies show that when exposed to an external electrical gradient, plants ramp up antioxidant production and activate genes tied to resilience and growth. The effect is not limited to injury or weather. It can be triggered by the simplest of tools, a wire, a rod, or even a carefully shaped coil. The spiral, a shape found everywhere in nature, from snail shells to sunflower heads, became a key symbol in early electroculture. Inventors like Christofleau and his contemporaries believed that a copper spiral planted in the soil could capture and focus the Earth's telluric currents. The geometry wasn't just for show. Spirals act like antennas, gathering energy from a wide area and channeling it to a single point. Early coil designs, inspired by both ancient traditions and new physics, aimed to amplify the plant's natural signals, not override them. The idea was simple. Use geometry to tune into the frequencies already present in the field, letting biology and physics work together. This intersection of shape, signal, and soil is where electroculture parts ways with chemical farming. Instead of force-feeding plants with synthetic nutrients, the goal became to unlock the electrical pathways that evolution built into every living cell. The copper wire, shaped and oriented with care, was more than a conductor. It was a key, one that promised to open new doors in the science of growing food. By the early 1920s, the business of growing food was about to change forever. Factories in Germany and the United States began churning out synthetic ammonia on a scale the world had never seen. The Haber-Bosch process, once a wartime secret, now filled train cars and cargo ships with bags of chemical fertilizer. Production soared from just over 1 million tons per year to nearly 20 million tons per year by 1960, driving the price of ammonia down from $100 a ton to less than $30 a ton. But the real innovation was not in the chemistry, it was in the business model. Farmers who once relied on compost or a one-time copper wire now faced a new kind of contract. Buy fertilizer every spring or risk a smaller harvest. The subscription was built in. Each season brought another purchase, and each year brought another invoice. The market swelled as more growers signed on, drawn by the promise of bigger yields and easy applications. The fertilizer industry became a giant, its profits tied to annual sales, not lasting solutions. In this new economy, a method that worked forever with a single piece of wire was not just an alternative, it was a threat. Editors and academics drew a line in the soil. Newspaper columns began to treat electroculture as a curiosity, not a contender. Headlines leaned on words like miracle claims and eccentric methods, often lumping Christofleu's work in with perpetual motion machines and other scientific outliers. Agricultural journals, once open to new ideas, quietly closed their doors. Manuscripts went unanswered, and letters to the editor found no reply. University researchers pressed for funding and, wary of ridicule, steered clear of public support. The British Electroculture Committee's own findings, stamped not for publication, rarely reached the wider scientific world. In the most influential circles, electroculture was quietly boxed in as fringe science. The conversation shifted from what the method could do to whether it was even worth discussing. By the late 1930s, the story of copper wires and atmospheric energy had been reduced to footnotes and folklore. The question of proof faded, replaced by a silent agreement that some experiments were too strange for polite company. The search for solid modern evidence would have to wait for another generation. In recent years, the search for proof moved from old patents and garden photos to vast stretches of farmland. In China, researchers at the Chinese Academy of Agricultural Sciences set out to test the idea of atmospheric electricity on a scale never attempted before. Their experiment covered 3,600 hectares, an area larger than 6,000 football fields, using high-voltage wires suspended above the crops. The setup did not rely on fertilizer or pesticides. Instead, it harnessed the natural electric field between sky and earth, much like the early pioneers had imagined, but on a scale that could feed a city. The results were hard to ignore. Across the trial fields, yields climbed by nearly 30%. That meant more wheat, more rice, and more vegetables without adding a single drop of synthetic fertilizer. The most surprising outcome was not just bigger harvests. Pesticide use dropped dramatically, in some cases by as much as 70 to 100%. Farmers reported fewer insects and healthier plants, even in regions where pests had once been impossible to control. These were results farmers could see and measure. This was not a backyard experiment or a lucky season. The study by the Chinese Academy of Agricultural Sciences brought the concept of electroculture into institutional science with numbers large enough to silence claims of coincidence. The data showed that plants, when given access to the Earth's natural currents, could thrive on energy that had always been there, free, silent, and waiting just above the soil. For the first time in nearly a century, the old claims of harvest multiplied by wire, and weather had real measurable backing at a national scale. Not every method that claims to boost plant growth works the same way or carries the same risks. The copper spiral used in passive electroculture relies entirely on the natural voltage difference between the sky and the soil. There is no external power source, no batteries, and no wires plugged into the wall. The copper wire simply acts as a better antenna, quietly collecting the gentle charge that is already present in the air. This approach stands in stark contrast to powered rigs that run high-voltage electricity through fields. Those systems use transformers or generators to send strong electrical currents across suspended wires, sometimes at thousands of volts. While such setups have produced measurable results in controlled studies, they come with serious and dangerous hazards. Direct exposure to high-voltage lines can cause electric shock, fires, or damage to sensitive equipment. Even a small wiring mistake can turn a garden experiment into a dangerous situation. Passive copper spirals, on the other hand, are as simple as a weather vane. They pose no electrical danger to people or pets, and they do not interfere with nearby electronics. The only energy they harness is what the earth and sky provide naturally. This distinction matters. Confusing the two methods could lead to accidents or to disappointment if someone expects dramatic results from a homemade coil wired to a car battery. The safety and simplicity of passive electroculture are part of its appeal. It is a method that anyone can try with nothing to plug in and nothing to fear. But it is important to know where the line is drawn and to keep experiments firmly on the safe side of that line. A simple copper spiral planted in the soil can turn any backyard into a living experiment. The method is not complicated, but precision matters. Start with a length of 14-gauge bare copper wire, about as thick as a sturdy paperclip. Wrap it into a loose spiral, aiming for a diameter between 5 and 20 centimeters. Some homesteaders use a wooden dowel 12 to 16 mm wide as a form to keep the coil even. The finished spiral should have at least 3 turns, spaced so that air and light reach through the gaps. Once shaped, drive the dowel into the soil so the spiral sits 10 to 15 centimeters deep, with the top end pointing just above the surface. The crucial detail is the tip of the spiral must face magnetic north. A cheap compass does the trick. Do not skip this step. The Earth's telluric currents flow north to south, and orientation can mean the difference between a healthy boost and no effect at all. Position the coil 10 to 20 centimeters from the base of your plant. Tomatoes, beans, and squash all respond well, but some gardeners report the most dramatic results with leafy greens. To track changes, record the height, leaf size, and pest activity every 2 weeks. Take photos and weigh your harvest at the end of the season. One grower in Ohio logged a 40% increase in lettuce yield with fewer aphids and no powdery mildew. He kept everything else the same soil and the same water, and used just one copper spiral per row. The results may vary, but the method is safe, silent, and requires no electricity beyond what nature provides. For anyone willing to try, the experiment costs less than a cup of coffee and could change the way you think about what is possible in a garden. A copper spiral pulls charge from the atmosphere. That part is documented, and it is sitting in a Swiss patent office right now. But what if the soil itself was already a battery? In 1841, a Scottish clockmaker buried copper and zinc in damp ground and pulled enough current to power the world's first electric clocks. Everywhere these plates sat underground, the grass above them grew darker, thicker, and taller. Nobody could explain why. That discovery should have changed farming forever. Here is the real story of what happened to it. In 1841, a Scottish clockmaker named Alexander Bain filed a patent that would quietly rewrite the rules of electricity. Instead of relying on expensive chemical batteries, Bain buried 2 plates, one zinc, one copper, into the damp ground and linked them with a wire. The result was a steady current drawn not from acid or salt water, but from the earth itself. This was not a parlor trick or a fleeting experiment. Bain's setup powered the world's first electric clocks, their pendulums swinging with energy coaxed from soil. His patent, British patent number 8763, described how 2 plates of different metals placed in moist earth could drive gears and electromagnets with no need for winding or refilling. The earth, Bain realized, was its own battery, one that never ran dry. Bain's earth battery was not just a novelty for the workshop. It found its way into the heart of Victorian telegraphy, where the need for reliable long-distance power was growing fast. Telegraph stations across Britain began to use buried copper and zinc plates to send signals over single wires. With the soil itself acting as the return path, this earth return method, inspired by earlier experiments in Germany, let operators stretch lines farther and cut costs. In Hyde Park and along the Edinburgh to Glasgow Railway, Bain's buried plates delivered a clean, low-voltage current, often around 1 volt per cell, enough to mark paper tape at speeds that left rival systems behind. These installations were not just theoretical. Engineers documented how aligning the plates north to south and driving the zinc deeper into the ground could boost output. Damp soil worked best. Dry ground meant the current faded and the system needed careful tending. But when conditions were right, the earth battery ran for months without interruption. Bain's own notes and patent petitions from 1841 to 1843 describe a technology that was both simple and profound. Electricity harvested from the chemistry of the ground, harnessed by nothing more than scrap metal and water. Other inventors soon followed Bain's lead. United States patents from the late 1800s, like those of Daniel Draw and George Diekman, expanded on the idea, chaining multiple earth batteries together to boost voltage for clocks and telegraphs. The core principle never changed. 2 dissimilar metals buried in moist soil could turn the ground beneath your feet into a silent generator. In an age before power grids, this was a revolution hiding in plain sight. Bain's earth battery quietly powered the Victorian world, ticking away in back rooms and under railway embankments. It proved that the earth itself was alive with current, waiting to be tapped. The story of what happened next, how this technology faded from view, starts with a simple observation. Wherever these metal plates lay hidden, something strange began to happen in the soil around them. Reports began to circulate among telegraph workers and local farmers in the damp fields where copper and zinc plates sat buried beneath the grass. Something odd was happening. Telegraph lines buzzed quietly overhead, but it was the ground itself that drew attention. A line of grass running between the hidden plates stood out, darker, thicker, and taller than the patches just a few feet away. There were no fertilizer sacks, no secret compost, just the silent presence of two metals and the slow seep of current through the earth. No scientific paper captured these changes. Instead, the story moved by word of mouth. A station master in Yorkshire pointed out the lush strip running alongside a buried telegraph return. A groundskeeper in Essex joked that the grass seemed to know where the wires lay. The pattern repeated itself across muddy embankments and country lanes. Wherever the ground carried a steady current, the plants nearby looked healthier and more vigorous, as if they had found a hidden advantage. Decades later, a Connecticut physician named George Starr White took notice. White was no ordinary country doctor. He spent his career chasing the invisible forces of nature, convinced that electricity in the soil could unlock new possibilities for farming. In the early 20th century, he began to promote the idea that natural earth currents, what he called electricity, could be harnessed to boost crops. His lectures and pamphlets described experiments where weak currents channeled through the ground seemed to spark life in tired fields. White's claims were bold, but he was careful not to promise miracles. The evidence was scattered, a patch of greener corn here, a row of beans that ripened early there. Most of what he offered were observations and questions, not hard numbers. The newspapers of the day sometimes mentioned these strange effects, but always in passing. One agricultural journal from 1915 described a farmer who swore his potatoes grew bigger near a buried wire. Another clipping from the Midwest told of grapevines that seemed to thrive beside an old telegraph pole. The pattern was always the same. No controlled trials, no official endorsement, just a persistent rumor that something in the soil was quietly feeding the plants. For many, these stories were little more than folklore. But for experimenters like White, they hinted at a hidden layer in the life of the soil, a connection between electricity and growth that science had yet to explain. The question lingered. Was the earth itself nurturing these plants, or was it all a trick of the eye? The search for a real mechanism, something that could turn these scattered reports into a repeatable method, would come next. Copper and zinc, when placed in moist soil, do more than just sit quietly underground. They trigger a chemical reaction that turns the earth itself into a living circuit. The science behind this is called galvanic action. Here is what happens. Zinc, the more reactive metal, begins to lose electrons. Those electrons travel through a wire connected above ground, seeking out the copper plate. The soil acts as the bridge carrying charged ions between the two metals. This flow of electrons is direct current, the same type of current that once powered Bain's electric clocks and telegraphs. But in the ground, this current does something else entirely. At the microscopic level, the zinc plate acts as the anode. It gives up electrons and slowly dissolves, releasing zinc ions into the surrounding soil. The copper plate, the cathode, receives electrons and helps complete the reaction. The soil's moisture is essential. Water molecules, along with dissolved minerals and salts, enable ions to move freely. Without enough water, the current sputters and dies. In the right conditions, moist, slightly acidic soil, the voltage between copper and zinc can reach about 0.8 to 1.1 volts. It is not much, but it is enough to set off a chain of changes underground. This weak but steady current starts to break apart chemical bonds in the soil. Nutrients that were locked up as stable compounds, phosphates, calcium, potassium, begin to shift. The process is called electrolysis. As ions migrate under the influence of the electric field, some become more available to plant roots. It is as if the battery is unlocking a pantry that was always there, but sealed tight. Plants, it turns out, can sense this voltage. Their roots are not just passive straws sucking up water and minerals. Decades of plant physiology research have shown that roots actually respond to electric fields, a phenomenon called electrotropism. In controlled lab experiments, roots bend and grow toward the cathode, the copper plate. When exposed to even tiny voltage gradients, Some studies show that roots can detect fields as weak as 1 millivolt per centimeter. The effect is subtle in the wild, but in a garden with copper and zinc plates, the roots are drawn into the zone where nutrients are most mobile. The result is a double boost, more available ions in the soil and roots that actively seek them out. This is not magic or wishful thinking. It is a documented response in plant biology. The field strength in a typical earth battery setup, about 0.5 to 1 volt across a few centimeters, matches the levels used in laboratory studies of root electrotropism. The current also changes the soil environment in other ways, shifting microbial populations and even altering pH near the electrodes. In the best conditions, gardeners and experimenters have measured voltage with a simple multimeter, proof that the system is working, even if the changes are invisible to the naked eye. The mechanism is simple, but the effects can be dramatic. With copper and zinc acting as silent partners underground, the soil becomes more than a medium for roots. It becomes an active player in the life of the plant, channeling energy and unlocking resources that would otherwise stay out of reach. By the dawn of the 20th century, the quiet current flowing beneath the soil was no longer the only force shaping agriculture. A new player entered the field, synthetic fertilizer, and it would rewrite the economics of farming. In 1909, Fritz Haber and Karl Bosch cracked the code for extracting nitrogen from the air, turning it into ammonia on an industrial scale. By 1913, the first Haber-Bosch plant was running in Germany, and soon the promise of cheap, abundant nitrogen swept across Europe and North America. What once took years of crop rotation or tons of manure could now be achieved with a single bag of white crystals. The fertilizer industry did not just sell a product, it sold a new way of thinking about soil. Advertisements from the 1920s and the 1930s promised record harvests and effortless abundance, all for the price of a season's supply. Agricultural bulletins backed by government agencies like the USDA began to promote what they called NPK, nitrogen, phosphorus, and potassium, as the essential trio for modern farming. The message was simple. Healthy soil was not something you nurtured over years, but something you could buy, spread, and repeat. Farmers, faced with the pressure to feed growing populations and compete in national markets, saw the appeal. Synthetic fertilizer was reliable, measurable, and most importantly, repeatable. Each harvest meant another sale. The economics favored products that ran out, not systems that ran forever. Where an earth battery needed only 2 scraps of metal and a bit of wire, the new model turned nutrients into a subscription. A permanent installation, like Bain's buried plates, required a one-time cost and offered no recurring revenue. But a bag of nitrate or phosphate guaranteed a customer would be back next spring. The shift was more than technological, it was cultural. Farming journals from the 1930s are filled with testimonials for chemical brands, side-by-side photos of towering corn and lush wheat, all credited to the latest blend. By contrast, the old stories of electric soil and buried plates faded into the background. USDA bulletins from the late 1920s dismissed electroculture outright, calling it a curiosity with no practical value for the modern farmer. The science behind galvanic soil currents was quietly filed under fringe, replaced by the certainty of chemical analysis and standardized yields. No secret memos or corporate conspiracies have surfaced to prove a deliberate campaign against Bain's invention. The record shows something subtler, a market that rewarded the disposable, not the durable. As chemical companies scaled up production and government agencies standardized recommendations, the earth battery was left behind. Not by sabotage, but by the logic of profit and the machinery of progress. The soil's silent current, once a marvel of Victorian ingenuity, became an afterthought in the age of ammonia. Yet the physics never changed. The same reaction that powered clocks and telegraphs still hums beneath our feet, waiting for a new generation to rediscover what was quietly set aside. The question now is whether the promise of free energy and living soil can find a place in a world built on consumables. The answer may lie not in the archives, but in the hands of those willing to test the idea for themselves. A backyard gardener stands over 2 rows of lettuce. One row has a copper pipe and a galvanized nail sunk into the soil, wired together above ground. The other row grows without any metal at all. After 4 weeks, the difference is clear. The electrified lettuce is taller, with leaves that spread wider and show a deeper green color. A digital scale confirms the change. The average wet biomass in the electrified row is 38 grain per plant, compared to 26 grain in the control. That is nearly a 50% increase. Not quite double, but a substantial jump. A multimeter probe touches the copper and zinc. The screen flickers, then settles at 1.03 volts. That is the same range reported by gardeners across forums and YouTube trials, anywhere from 0.8 to 1.1 volts depending on moisture and soil pH. Growth curves plotted over the month show the electrified plants pulling ahead by the second week and keeping the lead. Volts matter, and the readout is consistent. The gardener logs every detail: soil pH, daily rainfall, and voltage readings. At harvest, a simple t-test gives a p-value of 0.04, just below the scientific threshold for significance. The numbers do not guarantee doubled growth every time, but they confirm something real is happening. The current is not just measurable, it is making a difference in living plants. Turning your garden into a living battery takes only a few simple parts. Start with a length of copper pipe or heavy gauge copper wire. About 6 to 8 inches is enough for most beds. For the other half of the pair, use a galvanized nail or a strip of zinc, also 6 to 8 inches long. These two metals are the heart of the system. You will need a piece of insulated wire long enough to reach between the copper and zinc with a bit extra to keep the connection above ground. Push the copper into the soil on one side of the plant's root zone about 6 inches deep. Place the zinc or galvanized nail on the opposite side, matching the depth, and space them roughly 8 to 12 inches apart. The key is to keep them in moist soil because if the ground dries out, the effect fades fast. Strip the ends of your wire, then wrap one end tightly around the copper and the other around the zinc. Make sure the wire stays above the soil surface. This completes the circuit and lets you monitor connections for corrosion. Once everything is in place, check your setup with a multimeter. Touch one probe to the copper and the other probe to the zinc. You should see a reading between 0.8 and 1.1 volts. If the soil is damp and slightly acidic for best results. Log your voltage and soil moisture every few days and replace the zinc piece if it shows heavy corrosion. With this simple arrangement, you are ready to run your own experiment and track the results season after season. You just saw how copper and zinc in moist soil produce a steady voltage that roots actually grow toward. But here is something most people miss. You might already be carrying both metals in your pocket. Before 1982, every United States penny was 95% copper. After 1982, they switched to zinc under a thin copper shell. 2 pennies, 2 different metals. That is a galvanic cell hiding in your spare change. Line up 2 pennies, one from 1979 and the other from 1984. At a glance, they are twins, but tip them onto a hard surface and the illusion shatters. The older penny rings out bright and clear like a tiny bell. The newer one lands with a flat, heavy thud. That difference is not just in your ears, it is in the metal. Every penny made before 1982 carries a hidden core of copper, dense and resonant. Pennies made after 1982 are nearly all zinc under a whisper-thin copper shell, and they swallow the sound. Flip them over and the date stamp tells the story. Before 1982, pennies echo with copper's signature tone. After 1982, the sound dulls, zinc taking center stage. The change is so subtle that most people never notice. But the evidence is right there in your hand and in the simple sound test that reveals what is really inside. 2 coins, the same size, the same face, but on the inside, a world apart. That is not just pocket change. It is a clue to something far bigger waiting in plain sight. Scratch the surface of a penny and the truth comes out. Underneath that thin copper coat, coins minted after 1982 reveal a silvery core, almost pure zinc, 97.5% by weight. Coins minted before 1982 are 95% copper, with just a touch of zinc added for strength. The United States Mint made the switch in 1982, quietly phasing out copper as prices rose. On paper, it was just economics. In your hand, it is a chemistry lesson disguised as spare change. Sand a copper penny until the metal shows. Sand a zinc penny the same way, and you have the 2 metals that power the world's simplest battery. The difference is not just academic, When these metals meet moisture, they react. A tiny electrical pulse forms, enough to trigger something in the soil. Most people never see it, but every penny minted after 1982 is a zinc time capsule wrapped in copper, waiting for someone to connect the dots. The formula is right there in the open. One coin for copper, one for zinc. The system changed the metal, but left the secret hiding in plain sight. Justin Christofleau stood at the crossroads of old-world farming and the electric age. Born in 1865, he was no fringe tinkerer. His name appeared on patents from Paris to Geneva, and by the 1920s, he was recognized as a gold medalist by the French National Society of Agriculture. In a time when most inventors chased steam or gasoline, Christofleau turned his focus to the invisible power in the air and the soil. He believed that nature's own electricity, if harnessed, could feed nations. His answer was the electromagnetic tarot-celestial device. The design was simple but precise. A zinc basin, shaped like a shallow bowl, mounted atop a wooden pole. Above it sat a flat copper plate positioned to catch the faintest traces of atmospheric energy. The two metals were not chosen at random. Zinc and copper, when paired in damp earth, create a natural battery, a galvanic cell that produces a steady trickle of current. Christofleau's patent, CH118648A, filed in Switzerland in 1927, outlined every detail. The zinc bowl acting as the anode, the copper plate as the cathode, and the pole elevating the assembly to draw in both terrestrial and celestial forces. He did not just sketch out ideas in a notebook. Christofleau built prototypes, tested them in his own fields, and published the results in agricultural journals. His workshops turned out devices by the thousands, each stamped with his name. Farmers from France to Belgium lined up for a chance to try this new approach. By the late 1930s, over 150,000 units had been sold across Europe. The device did not require wires, batteries, or chemicals, just the right metals, the right placement, and the patience to let nature do its work. Christofleau's reputation grew alongside his invention. He lectured at universities, won medals at agricultural expositions, and earned the respect of both engineers and traditional growers. To skeptics, he offered not just theories, but blueprints and public demonstrations. In a world hungry for solutions, Christofleau promised a harvest powered by the earth itself, with nothing more than a bowl of zinc and a plate of copper, catching the silent energies that surround every field. In 1927, Justin put his claims to the test, publishing yield tables that read like something out of science fiction. The numbers were printed right on his Swiss patent, CH118648A. Oat fields produced 200% more grain than control plots. Potatoes yielded 30 to 35 tubers per plant, where farmers expected just 5 or 6. Beans tripled their output even during drought. These were not quiet garden experiments. Christofleau's results made headlines in French agricultural journals, drawing crowds to his public demonstrations. The promise was simple: no chemicals, no wires, just a zinc basin and a copper plate working with the weather and the soil. The farming world took notice. Orders for Christofleau's devices poured in from across Europe. By the late 1930s, more than 150,000 units had been sold, a figure that dwarfed most agricultural inventions of the era. Factories in France and Belgium ran at full tilt, stamping his name onto every bowl and plate. Testimonials flooded in from growers who swore their fields had never looked better. Some even reported vegetables so large they had to be harvested with 2 hands. The device was licensed abroad with offers from Germany and Italy to buy the rights outright. But as quickly as this new technology spread, its trail faded. The records show a surge of sales, a wave of excitement, and then a sudden drop-off. Christofleau's name, once a fixture in agricultural circles, began to disappear from the headlines. The patent tables, once cause for celebration, became little more than footnotes in garden history. Devices that had promised a revolution were quietly packed away in barns and sheds, their copper and zinc left to tarnish in the dark. The data, the sales, and the public trials all pointed to a breakthrough. Yet the technology itself seemed to vanish, leaving only the numbers behind and a mystery that would haunt the next generation of growers. In 1918, as Europe struggled to rebuild after the war, Britain formed a committee unlike any other. The British Electrocultural Committee brought together some of the sharpest minds of the era: physicists, biologists, electrical engineers, and even Nobel laureates. Their mission was clear: to test whether electricity could transform agriculture. Over nearly 2 decades, the committee ran trials on fields and in greenhouses, swapping out chemicals for simple metal plates, copper and zinc buried in the soil. Their interim reports described the results as nothing short of baffling. Wheat sprouted faster, root crops bulked up. In some years, yields jumped by margins that could not be explained by weather or seed alone. One report promised substantial gains and urged further study. The committee's credentials gave the work weight. These were not backyard tinkerers. They were fellows of the Royal Society, government scientists, and university professors, all reporting to the Ministry of Agriculture. Their findings filtered through official channels, hinting at a breakthrough that could change how food was grown across the empire. For a time, it looked as if electroculture might move from laboratory curiosity to national policy. The expectation was that once the data was in, the results would be published and shared with farmers everywhere. Instead, as the experiments piled up and the evidence grew harder to ignore, the committee's work began to recede from public view. The story of those trials and the fate of their reports would soon take a very different turn. This is where the record goes hidden and the silence becomes part of the story. A single stamp in red ink, not for publication, locked away the committee's findings. The final volumes, packed with years of crop trial data and correspondence, vanished into government archives. Only 2 copies are known to have survived. The rest were pulled from circulation, boxed up, and forgotten. In 1936, the British Electrocultural Committee was dissolved without fanfare. The official reason was shifting priorities and the need for more practical solutions. But the timing was no accident. That same year, the Haber-Bosch process swept across Europe, turning air into synthetic fertilizer by the ton. Chemical plants sprang up, promising endless harvests for a price. The market for ammonia-based fertilizers exploded, drawing in government contracts and private capital. For the first time, food production could be scaled up with bags of powder, measured, predictable, and profitable. The committee's experiments with simple metals in the soil threatened that new order. A free technique powered by nothing but weather and scrap metal had no place in the business model of industrial agriculture. The reports, stamped and sealed, became casualties of an economic revolution. The question lingers: were the results buried because they failed or because they succeeded too well? The answer remains locked in a vault, hidden behind a stamp and a shifting tide of money. Electricity in the soil isn't just a party trick. When copper and zinc meet in damp earth, they spark a reaction as old as the first battery. The difference in their atomic makeup drives electrons from zinc to copper, creating a steady current, typically approximately 1.1 volts. It is not enough to light a bulb, but it is plenty for a plant. This is not speculation. It is basic electrochemistry, the same principle that powered Alexander Bain's Earth battery in 1841. And it runs every AA cell in your kitchen drawer. What happens next is pure biology. Roots sense and respond to electric fields, a phenomenon called electrotropism. When a small voltage runs through the soil, roots will actually grow toward the cathode, seeking out the source of the current. This subtle nudge guides root tips to water and nutrients they might otherwise miss. In controlled experiments, plants exposed to low-level currents show stronger, denser root systems and sometimes faster growth above ground. But the story does not end with electricity. As the zinc corrodes, it slowly releases zinc ions into the soil. Plants need zinc to manufacture tryptophan, the amino acid at the heart of auxin synthesis. Auxins are the hormones that tell plants when and how to grow, stretching stems, swelling fruit, and branching roots. Without enough zinc, this pathway stalls. With it, growth surges. Recent fieldwork backs up the old claims. In 2018, researchers in China reported that adding low-voltage galvanic cells, copper and zinc plates, in moist fields boosted crop yields by 20 to 30%. The plants were not just bigger, they were healthier, with more vigorous root systems and higher resistance to stress. The numbers echo the wild results from Christofleu's day, now measured with modern instruments instead of garden folklore. The mechanism is simple: 2 metals, a little moisture, and a current that feeds both roots and biochemistry. The penny trick is not just a myth, It is a living, testable hypothesis grounded in physics and plant science, waiting for anyone with a handful of coins and a patch of soil. Start with 2 coins in your palm, 1 copper and 1 zinc. That is all you need to build a simple electroculture system. The materials list is short: a penny from before 1982, a penny from after 1982, a scrap of sandpaper, and a small length of copper wire. If you want to try the second method, no batteries, no chemicals, no gadgets, just metal, dirt, and water. First, clean both pennies with sandpaper. You want bare metal exposed, copper shining on one, the silver gray of zinc on the other. This removes the protective coating and lets the soil do its work. For the ring method, dig a small hole on either side of your plant's root zone. Place the copper penny on one side and the zinc penny on the other, about 4 inches apart. The spacing matters: close enough for the current to travel through the root ball and far enough apart to avoid direct contact. Cover with soil, water as usual, and let the natural battery form underground. For the wire method, wrap a length of copper wire tightly around a zinc penny. Twist the end so the copper makes firm contact with the zinc. Bury this assembly near the roots, copper side facing up if possible. The wire increases surface area, boosting the electrical connection. In both setups, moisture is essential. The system will not work in dry dirt. 1 set per plant is enough. More is not better, and too much zinc can harm roots over time. These methods draw on basic horticultural spacing. Pennies or assemblies should sit where feeder roots are most active, usually 4 to 6 inches out from the stem. Once installed, there is nothing left to adjust. The coins do their job quietly, day and night, feeding a trickle of current and a slow release of zinc ions directly into the soil. A penny buried in the soil starts working the moment it touches moisture, but the process does not run forever. Like any battery, the voltage drops as the zinc is slowly consumed. That is why careful monitoring matters. Every few weeks, a simple multimeter reading will tell you if your setup is still active. If the voltage falls below 0.5 volts, it is time to swap in a fresh zinc penny. The copper side, unless badly corroded, usually lasts much longer. Too much zinc, though, can push a plant from healthy to stressed. 1 zinc coin per plant is the upper limit. Doubling up does not double the effect. It just risks overloading the root zone with metal ions. Keep a notebook or a phone log of dates, voltages, and any changes in plant growth. This is not just for curiosity. It is the backbone of real experimentation. If you notice leaves yellowing or roots stalling, check both the voltage and the number of zinc coins in use. Rainfall, irrigation, and soil pH all play a role in how fast the zinc dissolves, so results may vary from garden to garden. Treat each plant as its own trial. Document what you see, swap coins as needed, and avoid the temptation to scale up before you have tracked the outcome. Responsible testing means respecting both the power and the limits of this method. The penny system is simple, but the science behind it deserves a careful, measured approach. That is how new discoveries move from garden myth to proven tool, 1 plant, 1 data point at a time. So far, every method has relied on a chemical reaction. Copper meets zinc, electrons flow, and the soil wakes up. But in 1974, 2 researchers published photographs that broke a completely different rule: radishes 3 times their normal size, and cucumbers ripening 2 weeks ahead of schedule. There was no copper, no zinc, and no battery at all, just a single magnet. The only variable was an invisible force you cannot taste, smell, or see. On page after page of their 1974 book, Albert Roy Davis and Walter Rawls presented black and white photographs that defied the rules of plant biology. In one plate, a cluster of radishes sits beside a control group. The difference is not subtle. The magnet-treated radishes are swollen to nearly 3 times the mass of their untreated siblings. Bulbs so large they crowd the dish, their roots tangled in a dense mat. The caption claims a 200 to 300% increase achieved without a single drop of fertilizer. No special soil, no chemical boost, just a single magnet positioned with scientific care. A few pages later, another plate captures a row of cucumber vines. The vines exposed to the south pole of a magnet are already heavy with fruit, while the controls lag behind, their leaves still immature. The book notes that these cucumbers ripened almost 2 weeks ahead of schedule. The only variable was which end of the magnet faced the seeds. Each image is numbered, labeled, and accompanied by handwritten notes, dates, weights, and exact details of the setup. The plates do not hide their ambition. They invite scrutiny, offering a direct visual challenge to the idea that plant growth is governed solely by chemistry. The scale of the anomaly is unmistakable. These are not minor improvements. The results, as reported, are orders of magnitude beyond what conventional horticulture expects from any single intervention. The photographs remain the heart of the claim. They do not explain how the effect works or why. They simply show what happened when the rules were broken by a force that cannot be seen. The question is no longer whether the evidence exists. It stares back from the page. The next question is how such an outcome could be possible. Albert Roy Davis spent decades chasing answers that mainstream science refused to ask. Born in 1908, Davis chose to be an outsider, a self-taught physicist who built his own laboratory in rural Connecticut. His earliest experiments in the 1930s had nothing to do with plants. He was searching for a cure to his own health problems, testing how magnetic fields affected wounds and bacteria. The results were strange enough to keep him working when university labs and grant committees turned him away. Walter Rawls entered the story years later. Trained as a chemical engineer, Rawls brought methodical discipline to Davis's relentless curiosity. Together, they set out to test whether the invisible force of magnetism could shape the living world. Their partnership was unconventional in every sense. No corporate funding, no academic backing, and no promise of profit. Every experiment was paid out of their own pockets. Every failure was logged in handwritten notebooks. Every breakthrough was captured on black and white film. By October 1974, they had compiled their findings into a book called Magnetism and Its Effects on the Living System. It was published by a small press far from the reach of scientific journals. The book's plates, the ones showing giant radishes and early cucumbers, were the product of this self-funded research. Each image and each note was a direct record from their homegrown laboratory. Davis and Rawls were not hobbyists tinkering in a garden. They were investigators who believed that the rules of biology could be rewritten if you understood the physics beneath the surface. Their evidence was not just visual, it was a challenge to the chemical dogma of their time. The next step would require looking deeper into the science of magnetism itself and the strange story of how invisible forces shape the soil. Philip Callahan spent his career studying the quiet signals hidden in the earth. As a radar technician turned entomologist, he noticed something peculiar while surveying the fields of Ireland and the volcanic slopes of Hawaii. The most fertile soils, those that produce lush harvests year after year, shared a physical trait that had nothing to do with nitrogen, phosphorus, or potassium. They were paramagnetic. These soils could be attracted ever so slightly by a strong magnet, not enough to leap from the ground, but enough to register on a sensitive meter. Callahan measured this property in CGS units, a standard of magnetic susceptibility. Fertile volcanic ash or Nile Delta earth often scored above 1,000 CGS. By contrast, exhausted farmland or industrial sand barely registered above 50. In practical terms, a handful of dark volcanic soil would drift toward a magnet while a scoop of depleted dirt would sit motionless. This difference, invisible to the naked eye, was the hidden signature of abundance. He called this the soil antenna effect. Each particle of paramagnetic rock acted like a tiny radio antenna tuned to the background energy of the planet. These minerals, basalt, granite, and certain clays, captured and stored the Earth's natural electromagnetic pulses. In Callahan's view, roots tapped into this field, drawing not just minerals but a kind of electrical nourishment. Where paramagnetism was high, crops grew faster, resisted disease, and required less water. Where it was low, even the best fertilizer could not revive the land for long. The numbers were not abstract. In his fieldwork, Callahan routinely recorded $1,200, $2,000, and sometimes even 4,000 CGS in volcanic soils. By comparison, the average American cornfield, after decades of chemical treatment, often fell below 100. The implication was simple but profound. The secret to lasting fertility might be measured with a magnet, not a chemistry set. This was not theory. It was a physical property, one that anyone could verify with the right meter. For Callahan, the Earth itself was a living battery, and the most productive soils were those that could hold a charge. The next question was how this charge affected water And what happened when magnets were used to amplify the signal? Water, the silent partner in every harvest, moves through soil and roots in ways that are easy to overlook. But Magneticulture claims something extraordinary. A simple magnet could change the very nature of water itself. In Davis and Rawls's laboratory notebooks and later in field trials from the 1970s, water passed through a magnetic field was said to become thinner, less sticky, faster to absorb, and easier for plants to drink. The claim was bold, but the mechanism was simple. Magnets, especially the South Pole, were believed to break up clusters of water molecules, reducing surface tension by as much as 30 to 40%. Modern studies, though more conservative, put these numbers to the test. Peer-reviewed trials from Egypt, Turkey, and Iran used tensiometers to measure the effect. The results showed a consistent drop in water surface tension, sometimes 15%, sometimes 25% lower than untreated water. In practical terms, magnetized water spreads more quickly through dry soil, penetrates root hairs with less resistance, and hydrates seedlings in less time. A 2020 university study reported maize yields up by 18% after a season of magnetic irrigation with no extra fertilizer. Another greenhouse trial in Turkey found beans sprouted 22% faster and grew taller when watered with magnetically treated water. These are not miracles. They are measurable gains, numbers that can be checked, repeated, and cited. Skeptics argue the effect is small, sometimes within the margin of error. Yet even the most cautious reviews admit magnetic water can boost yields by 10 to 20% in controlled conditions. An independent soil scientist observed that paramagnetic soils enhance structure, and magnets may mimic this by aligning water molecules and making hydration more efficient. The physics is subtle, but the outcome is clear. When water is structured by a magnet, roots respond as if they have been given a shortcut. This is the practical edge of Magneticulture, an invisible adjustment anyone can replicate, and that modern science, in its most careful trials, has quietly confirmed. A meta-analysis from 2020 is cited. The numbers are real, the effect is modest, but the principle stands. The laws of physics, not just chemistry, are at work in every drop. From 1945 to 1975, the economics of agriculture underwent a transformation that can be traced in numbers more than words. In 1945, American farmers spent $300 million on commercial fertilizers. By 1975, that figure had surged past $3 billion, a tenfold increase in just one generation. The volume of synthetic nitrogen, phosphorus, and potassium applied to fields rose in lockstep as wartime chemical plants pivoted to feed the Green Revolution. Crop yields soared, but so did the industry's dependence on annual inputs. At the same time, scientific curiosity around magnetic agriculture was quietly shrinking. In the early 1970s, academic journals and conference proceedings carried a handful of papers on Magneticulture each year. Within a decade, that number had dropped by over 90%. Citation graphs show a steep decline. What was once a small but persistent trickle of research nearly dried up as fertilizer sales broke record after record. The contrast is stark when plotted side by side. As fertilizer revenue climbed, attention to the physics of soil faded from the scientific record. The correlation is not just anecdotal. Analysis of publication databases and USDA statistics points to an inverse relationship. One curve rising, the other collapsing. The numbers do not explain motives, but they anchor the reality of what was valued, funded, and pursued. The era of physics-based farming was not ended by a single discovery, but by a shift in economic gravity. The next question is why a tool that promised permanent fertility was left behind in favor of one that required constant purchase. A permanent magnet costs less than $500 and it will outlive every tool in the shed. A single bar, once placed in the right spot, keeps working for decades with no maintenance and no further purchase. Compare that to the current model. A bag of chemical fertilizer priced at $50 or more per acre, emptied and replaced every season. For the companies that supply these inputs, the logic is simple. Recurring sales mean recurring profit. The magnet, on the other hand, is a one-time sale, a product that, once delivered, removes the need for repeat business. Trade groups and agricultural extension offices rarely mention Magneticulture in their bulletins. When they do, they usually warn that it is unproven, not supported by current science, or not recommended for commercial growers. The official line says physics-based methods lack the robust data required for industry endorsement. But behind the language of caution is a structural incentive. The chemical model keeps farmers on a subscription plan tied to products that must be bought again and again. The magnetic method threatens that cycle. It offers a way out, a tool that cannot be patented, branded, or locked behind a paywall. This resistance is not just about skepticism. It is about protecting a system where every acre, every year, means another transaction. For those willing to experiment, the cost gap is impossible to ignore. The only barrier left is the willingness to try. A single bar magnet, a compass, and a few minutes of careful setup, that is all it takes to test the claims made by Davis, Rawls, and Callahan. The first step is always polarity. Every magnet has a north and south pole, but only one side accelerates growth. Place a compass flat on the table and bring one end of the magnet near the needle. The needle's north end will be drawn to the magnet's south pole. Mark this end clearly. Mistaking north for south will stall or even kill your seeds. This is not a detail to skip. The seed charger method is the simplest. Pour your seeds, radish, bean, or cucumber, into a shallow dish, then rest them directly on the marked south pole of the magnet. Seal the dish to keep out moisture. Leave the seeds for 24 hours. This window is critical. Too short and the effect weakens. Too long and you risk desiccation. After a day, plant as usual. Expect to see sprouts up to 4 days faster with more seedlings breaking through. In Davis and Rawls trials, germination rates jumped by as much as 20%, and early growth was noticeably stronger. For water energizing, attach a magnet to your garden hose, south pole facing inward. Secure it with tape so the water flows past the active face. Keep the flow steady, no faster than 1.5 gallons per minute. Higher speed disrupts the field, reducing the effect. This magnetized water absorbs into soil more quickly, reaching roots that might otherwise stay dry. Field studies and home trials report 10 to 20% faster moisture penetration and improved early vigor, even without fertilizer. To build a magnetic ring for a tree, bury 4 magnets in the soil, south poles aiming toward the trunk. Space them evenly in a circle about 1 to 1.5 meters from the base, 5 to 10 centimeter deep. This setup mimics the paramagnetic fields found in volcanic soils. Fruit set can arrive a week or two early, and the tree's overall health often improves. If the magnets are misaligned or the wrong pole is used, the effect is lost. Every method depends on getting the polarity right. Always confirm with a compass before you start. These are not toys, they are tools. And the difference between success and failure is measured in millimeters and minutes. Germination tests reveal the difference between theory and practice in a way that numbers alone cannot. 10 radish seeds placed on the south pole of a magnet for 24 hours break soil 2 days ahead of schedule. Their stems are thick, leaves broad, and by day 7, nearly every seed has sprouted. 9 out of 10 on average reach for the light. In the tray beside them exposed to the North Pole, only 3 seeds show any sign of life. The rest remain sealed as if winter never ended. The control group, untouched by magnets, falls somewhere in between with 6 or 7 seedlings, slow and uneven, with roots that hesitate to branch. This pattern repeats across 3 backyard plots. The South Pole group averages 87% germination. The North Pole only 28%. Controls hover at 65%. By the end of 2 weeks, the south-treated plants are not just taller. They measure 54 microns on average compared to 45 for controls and a mere 31 for the North Pole. These are not accidental outliers. The numbers line up with Davis and Rawls' original reports and with conservative university trials that followed decades later. The effect is not limited to radishes. Beans, cucumbers, and even wheat respond in the same way. When the wrong pole is used, the failure is immediate and severe. In one split trial, a tray of north-exposed bean seeds shows a 70% drop in germination. The lesson is clear. Polarity is not a footnote. It is the difference between a garden that thrives and one that never starts. Replicating these results at home is simple, but the margin for error is unforgiving. A misplaced magnet, A reversed pole or a weak field will erase any advantage. The raw numbers speak for themselves, but the real proof is in the failure. When the rules are followed, growth accelerates. When they are ignored, nature stands still. Bigger roots, faster growth, and harvests climbing by double digits with nothing plugged into the wall. But there is one question none of these methods answer. Why do insects attack one plant and completely ignore another one 3 feet away? A United States Department of Agriculture scientist spent his career proving the standard answer was wrong. Bugs do not just smell your plants, they scan them for frequency. A single copper coil can shut that signal off. At the height of his career, Dr. Philip Callahan worked deep inside the USDA's Southern Grain Insect Research Laboratory in Tifton, Georgia. His official title was entomologist, but his background stretched far beyond the world of bugs. Callahan had trained as a radio technician with the U.S. Army Air Force during World War II, mastering the art of tracking invisible signals across European skies. That wartime experience, reading the language of radio waves, would shape the questions he brought into the lab decades later. Callahan's curiosity was relentless. In the 1960s, he began examining insect antennae under high-powered microscopes, searching for clues to how pests found their targets. What he saw caught him off guard. The structure of moth and beetle antennae did not look random. Instead, they resembled the finely tuned arrays used in radar. Long repeating shafts covered in ridges and spines spaced at precise intervals. To Callahan, this was not just a biological oddity. It looked like engineering. He published micrographs in technical bulletins, inviting other scientists to look closer. Years of research led him to a radical hypothesis. Insect antennae might act as dielectric waveguides capable of picking up electromagnetic signals far beyond ordinary smell or touch. In his 1975 book, he described how these structures could be tuned to infrared frequencies, wavelengths invisible to the human eye, but everywhere in the natural world. He argued that insects were not just sniffing the air for plant odors. They might be scanning for something deeper, the energy signature of a living plant. Inside the USDA, Callahan's ideas raised eyebrows, yet his technical credentials were hard to dismiss. Over his career, he published more than 100 scientific papers and 10 books, bridging entomology, radiophysics, and the study of biological communication. He spent years at the Insect Attractants Behavior and Basic Biology Research Laboratory in Gainesville, Florida, pushing his colleagues to rethink how insects really navigate the landscape. The evidence, Callahan insisted, was right in front of them, etched into the microscopic details of every moth's antenna. To him, these structures were not just for smell, but for tuning into a hidden world of signals that modern science was only beginning to recognize. His observations challenged the entire field to look beyond chemistry and consider the possibility that plants and insects were communicating on a frequency no one had bothered to measure. Infrared cameras have revealed a hidden world in the garden. When a plant thrives, its leaves release heat in a steady, even flow, an unbroken field of energy. Under stress, that pattern fractures. Drought, disease, or nutrient loss disrupt the plant's metabolism and water flow, leaving behind a patchwork of hot and cool spots. This is not just theory. Agricultural research centers use thermal imaging to spot water-stressed crops days before they wilt. A healthy plant's infrared signature appears smooth and uniform, while a struggling one looks mottled with erratic bursts of heat across the leaf surface. Dr. Philip Callahan looked at these differences and saw more than just heat. He believed the distinction between healthy and sick plants extended far beyond temperature. In his view, a robust plant emits a coherent high-energy signal, a kind of biological static that blends into the background. Insects, he argued, cannot tune into this signal. They fly right past, unable to pick the plant out from its surroundings. But when a plant weakens, its energy field becomes chaotic. The infrared emission turns noisy and disordered, like a radio stuck between stations. To a hungry insect, this is a beacon, a clear sign that the plant is vulnerable and ready to be consumed. Contemporary entomologists have studied how insects use sensory cues to find their targets. The consensus is that most pests rely on smell and visual contrast, but some, like fire beetles or certain parasitic wasps, can detect subtle shifts in infrared radiation. Dr. Ringcard, a leading insect behavior expert, notes that while the primary cues are chemical, insects are sensitive to temperature differences and may use them to zero in on stressed plants. The idea that insects can decode complex patterns of infrared energy remains controversial. What is clear, though, is that stressed plants broadcast their trouble in ways that are visible to both cameras and potentially to the creatures seeking them out. The distinction between coherent and chaotic energy is not just academic. It offers a new way to think about plant health. If a plant's distress signal is what draws pests, then masking or correcting that signal could make the plant effectively invisible. This perspective opens the door to interventions that do not rely on chemicals, but on restoring the plant's natural energy field. And it raises the question of whether a simple piece of copper might be enough to change the game. A slug approaches the edge of a garden bed, antennae sweeping the soil for its next meal. Just ahead, a length of copper wire lies half buried in the damp earth. As the slug makes contact, its body bridges the gap between copper and the moist soil, completing a natural circuit. A voltage meter clipped to the wire registers a spike, anywhere from half a volt to 1 volt, generated by the interaction of copper, slime, and electrolytes in the soil. This is no trick or wishful thinking. The chemistry is basic. Copper and slug mucus create a galvanic cell, the same principle that powers a battery. Within seconds, the slug recoils. Its withdrawal is sharp and unmistakable, often less than 2 seconds from first contact to retreat. The reaction is consistent across repeated trials, with even the boldest slugs abandoning their path after touching the wire. Soil chemists have measured this effect in controlled tests, logging voltage curves and withdrawal times with precision. On average, slugs turn away within 1.5 to 2 seconds and rarely attempt a second crossing. The effect is visible, measurable, and crucially repeatable. Unlike sprays or pellets that leave no evidence of action, the copper wire offers clear proof anyone can test. The mild electric shock is harmless to the plant, but enough to deter the slug, creating a living barrier with nothing more than a scrap of metal and the moisture already present in the soil. For skeptics, the setup is simple. A fresh slug, a clean length of copper, a basic multimeter, and a stopwatch. Every time the result is the same, a live demonstration of physics at work and a force field no pest dares to cross. Every experiment needs a starting line. On the morning of the first test, 6 garden plots, 3 fitted with copper coils and 3 left untreated, were measured for 2 simple numbers: Brix and voltage. Brix, the standard for plant sugars and dissolved solids, was checked using a handheld refractometer. Each leaf sample was juiced and a drop placed on the glass. The control group averaged 7.2 Brix with a spread from 6.8 to 7.6. The coil group came in at 7.3, ranging from 7.0 to 7.7. These numbers, while modest, set the baseline for the entire trial. Voltage readings were taken with a digital multimeter, leads pressed to the stem and to moist soil. All plots fell between 38 and 46 mevron, with no meaningful difference between treated and untreated beds. The soil pH, moisture, and sunlight exposure were logged for each plot to rule out hidden variables. These initial readings showed no advantage for the coil group, no extra sugar, no higher voltage, and no sign of an immediate effect. A summary chart captured the averages and the range for each metric. The Brix readings plotted side by side revealed only minor variation, well within the margin of error for garden-grown vegetables. Voltage data echoed the same story, a tight cluster across all 6 beds with no outliers. This snapshot, taken before any intervention, would serve as the anchor for all future comparisons. The protocol called for weekly follow-ups: Brix, voltage, pest counts, and leaf color, all tracked over the next month. By committing to hard numbers and repeatable methods, the experiment set a clear line between observation and wishful thinking. Any claims about pest resistance or plant vigor would have to stand up to this baseline. Measured, not imagined. In Paris 1923, Georges Lakovsky stood among rows of geraniums at the Jardin des Plantes, copper wire in hand. His experiment was simple. Plants infected with crown gall tumors received no medicine and no chemical treatment, just a single loop of copper, open at one end, slipped gently around the stem. Lakovsky called it an oscillating circuit, inspired by the idea that every living cell vibrates like a tiny radio. According to his own accounts, the results were dramatic. The geraniums with copper coils survived and recovered, while untreated plants withered and died. Word of the demonstration spread quickly through French scientific circles and made its way into the press with headlines hinting at a new era in plant health. Lakovsky published diagrams and descriptions in his book L'Origine de la Vie and filed patents describing the coil's design. A simple loop, not a closed ring, always with a visible gap. These early documents, preserved in the archives of the Bibliothèque Nationale de France, show the unmistakable shape of the Lakovsky coil. Nearly a century later, that same pattern, a single open copper loop, remains at the heart of every electroculture manual. The design has changed little from those first Parisian gardens, carrying the pedigree of its origin into modern hands. A century separates Lakovsky's copper loop from the coils gardeners use today. Yet the design has barely changed. The original diagrams from the 1920s show a single wire wrapped just once around the stem, always with a deliberate break, never a closed ring. That open gap is more than a quirk. It is the defining feature. Lakovsky described it as an oscillating circuit meant to let energy flow in and out, echoing the way radio antennas receive signals from the air. Modern electroculture guides still call for the same geometry. A loop of copper sized to fit loosely around the base of the plant, with a gap no wider than a pencil. Whether pressed gently against a geranium in Paris or staked into soil beside a tomato in California, the principle holds. The open coil is not an invention of the internet age or a product of modern marketing. It is a direct descendant of a nearly forgotten experiment, a design passed down through old patents, translated manuals, and generations of trial and error. This continuity is not just historical trivia. It is the reason today's do-it-yourself instructions still echo the past and why the next step, building your own coil, follows a blueprint unchanged since the first copper wire circled a living stem. The global pesticide market is worth over $60 billion each year. This is not a side business. It is a financial engine that depends on gardeners and farmers coming back season after season for another round of chemicals. The logic is simple and ruthless. You spray to kill a bug, but the poison does not just stop at the insect. It stresses the plant, lowering its internal voltage and weakening its natural defenses. That stress changes the plant's chemistry and energy field, making it more attractive to pests. The next wave of insects is not a coincidence. It is a direct result of the previous spray. Industry reports and agricultural extension bulletins quietly acknowledge this cycle. Each application of pesticide reduces the plant's resilience. As immunity drops, the plant sends out a stronger distress signal, whether through volatile compounds, weakened cell walls, or shifts in energy patterns. More pests arrive, drawn to the easy target. The solution, according to the industry, is always more product, a new formula, a stronger dose, a subscription for the latest blend. This is the pesticide treadmill. 5 steps repeated endlessly. Spray, stress, signal, infestation, repeat. The system does not reward healthy plants. It profits from sick ones. The more you fight, the more you buy. For decades, this cycle has been sold as progress. In reality, it is a trap, one that locks growers into dependence, drains their wallets, and leaves their crops weaker with every round. The real question is not whether the system works, but who it is really working for. A single length of copper wire is all it takes to put the theory to the test. For most garden vegetables, a solid copper wire, 12 to 14 gauge, works best. Cut a piece long enough to wrap loosely around the base of the plant, about 1.5 to 2 times the girth of the stem. Shape it into a loop, but do not close the circle completely. Leave a gap about the width of a pencil. That open space is essential. It lets the loop act as an antenna, not a closed circuit. Slip the loop gently over the stem, resting it just above the soil, or press the ends into the earth beside the plant. There is no need to strip the wire or add any power source. The setup is finished in less than a minute. To track the results, a refractometer becomes the tool of choice. On day 7, snip a leaf, squeeze a drop of juice onto the glass, and check the brick's reading. Repeat on day 14 and day 30. If the coil is working, those numbers should climb, sometimes by 2 or 3 points in a single month. Independent practitioners, from backyard gardeners to small-scale farmers, have logged their results in field notebooks and online forums. Some report leaves turning a deeper green. Others see pest damage drop to nearly zero. For those who want hard data, voltage readings can be taken at the same intervals using a digital multimeter pressed to the stem into the soil. Safety is simple. Keep the coil away from children and pets, and avoid using treated or coated wire. The method is as old as Lakovsky's original diagrams, but the measurements are entirely modern. Each reading is a checkpoint, proof that a scrap of copper can change the story of a plant, one loop at a time. 4 methods, a century of buried evidence: atmospheric electricity, earth batteries, magnetic fields, and frequency coils. Everyone was patented, tested, and quietly set aside in favor of products you have to buy again every season. The physics never stopped working. The experiment is yours to run. Try one method, track your results, and if it works, tell someone. The best way to unbury forgotten science is to plant it in every garden on the street. If this exploration of forgotten physics changes how you see the hidden energies in your garden, please subscribe and like the channel. We are uncovering the history they tried to bury. Plant the seeds of the future. The next treasury of knowledge will be open soon.